Today I'm going to be demonstrating all the essential steps needed to construct a scatter plot using mass and volume data as an example. Students should have an example set of data from their investigation of the density of a cylinder, and your graph paper will look somewhat different than mine based on the number of boxes or intervals that you have compared to mine also. The first thing you guys need to do is look at the top left part of the screen and see all the essential steps we need to complete today. You guys need to start by labeling the y and the x axes. If you don't remember, the y-axis is the vertical axis over here that goes in this direction. The x-axis is over here and it goes along this way. After you label those axes with the quantities, the type of measurement that you're getting, you move on to scaling the axes. You need to scale the lines, the boxes, or what I call the intervals, with an appropriate number that spreads the data out throughout most of the graph. Then you can plot the data, place a best fit line that best fits the data, and then determine the slope of the line, and finally identify the y-intercept. So the first thing you guys should be doing is writing that the y-axis is the mass, and I'm going to put my units on there also, measured in grams. The x-axis is volume, and you can abbreviate the mass with an M and the volume with a V, and your volume is going to be in centimeters cubed. So your graphs must have this labeled, folks. Next on the list is actually scale the intervals. Now, in order to scale the intervals, or those increment marks, the lines that go along here, you first need to count the full amount of intervals on this graph paper or on your graph paper. So when you start, you do not count the first line at the origin. You're going to jump over to the first one, and this first jump is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I like to make a mark at 10 in case I lose count. I can go back to just 10, and then I got 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. I'm just going to make a note off to the side of my graph paper. There's 23 intervals on the x-axis. Now we need to do the same thing to the y-axis. Jumping to the first interval, I'm going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I'm going to make a mark so I don't lose count. 11, 12, 13, 14, 15. And I'm going to write that off to the side so I don't forget how many intervals we have. Now what we need to do is find the largest data for the y and the x axis from your data table. And we're going to use that and divide the max data by the number of intervals on each axis to get an estimate or a suggestion for how we should label each interval on the axes. So for example, on the y-axis, mass, my max data is 71.27 grams. And I'm going to divide that by the number of intervals, and it was 15. When I divide that out, I get a number that's 8.64. And what that means is that every interval can be worth 8.64 grams for every one interval. You got to stretch out the data as best you can, but you got to also have big enough intervals that your data, it does not fall off the graph. Now this is a suggestion and you cannot go any lower than this. Some people might say they're going to scale their graph by 8. So they'll go 8 over here and then 16 and add those up. But if you do that, not all your data will fit on the graph, so you cannot do that. This is just a recommendation. And so you must round up to the next best number. Some people could go by 9 and round up here, but I think we're close enough to 10 that 10 will be okay. So I'm going to go by 10 grams for every interval. And I'll scale that once I get the other one calculated as well. So that's for the Y. This is just for my graph. Your graph will have a different number of intervals and will be labeled with a different number most likely. On the x-axis, I had the max volume of 8.25. So for the x-axis, I need to take that 8.25 grams and divide it by the number of intervals that we counted was 23. When I divide 8.25, which was my max volume, by the 23 interval boxes, I get 0.36 grams every interval. Now scaling by 0.36 would be a nightmare, so we need to round up to the next best number. You cannot round down to 0.3, you must round up. Some people might want to go by 0.4, and that's totally fine. That's probably the best choice. For this video, to make the scaling easier for demonstration purposes, I'm going to go and jump this up to 0.5 grams. For every one interval. So I'm going to scale my graph on the y-axis by 10s, and I'm going to scale my x-axis by 0.5s. And when I do this, I'm going to zoom in so I can better write on the graph. You guys can rotate your paper and better handle it when you're doing this live in person. All right, make sure you guys also mark where your 0 mark is. So starting at 0 on the x-axis, I said I was going to increase by 0.5 every time. So I'm going to label 0.5. And then 2. In some cases, you guys can be clever enough to just start skipping a couple boxes and just go by like the whole number. So maybe skip 3.5 and write 4 down on the next one. But for the demonstration purpose here, I'm going to go ahead and write them all as best I can. I just completed scaling the entire x-axis, going by 0.5. I'm now going to move on and start to scale the y-axis. And if you remember previously in the video, we talked about scaling it based off the suggestion of 8.64, but I'm going to go ahead and round that up to 10. So I'll start this and pause the video and have it completed and move on. I just completed scaling the rest of the y-axis using the scale of going by 10s for every interval. Now I've got both my axes labeled with mass and volume and the units, grams and centimeters cubed, and I've also got them labeled with the intervals on the x of 0.5 and then on the y-axis 10. And remember, I got those intervals by doing the max data divided by the number of intervals for every axis. The next thing we need to do on our list is plot the data as carefully as we can. So in pairs, X and Y are pairs and they go together. They're partners in crime. So I'm going to place them as best I can on the graph. So I'm going to go and find approximately where 71.27 is. But the graph is scaled so large that I don't even really know where the 10th places are or the hundredths places. So the 0.27 doesn't really matter much at this point. I'm simply going to find approximately where 71 is, and then I'm going to match it up with the 8.25 as best I can. Now I know 8.25 is in between the 8 whole and the 8.5, so I'm going to try to make that halfway and place a dot as best I can. So now let me go a hair over it, so it's 71. Because between 70 and 80, I got to imagine there's 71, 72, 73, and so on. So I'm going to go a hair over it. And it's in between the 8 and the 8.5. Next, I'm going to move on. I'm going to find approximately where 60.48 is, and then its partner 7. So here's 60, and it's 0.48, so that's really tough to imagine being too far beyond the line. So I'm placing it as close as I can. The next one, 52.71, and I'm going to try to find its partner, 6.19. Here's 6. 6.19 is barely over that 6 mark. 52. I know 55 is about halfway, so I'm going to go 52 right about here. And now I got to tell you guys, the data points do not necessarily always land on one of these grid lines. You put them where you best estimate that number to actually be. The last one, 42.3, and its partner 5. So 5 is right on the line, which is easy to find. But now I need to estimate approximately where 42.30 is. So there's 4 data points. That's kind of the minimum amount of data points we need to get a scatter plot going. Now already I can tell that these data points line up in a pattern where a line could basically pass through or near them all. So now I'm going to go over to the next step and place a best fit line. The line doesn't look to be like it's going to be curved. It looks like it's going to be a straight line, which in our class and in math classes, you guys should know, is a linear line. So I'm going to do my best to line this line up so it goes through the data points. It is a major error or misconception. People will think down here at the origin, where my cursor's at, that the line needs to go right through the corner there. That is not true. Do not purposely put your line through the origin because you think it needs to go through the origin. Sometimes it just happens to go through there and it makes sense based on what you're measuring. And I'm going to extend my line all the way out past the data. I'm placing this line so it best fits these 4 data points. It just so happens that it looks like it goes through or near the origin. So everyone's graph should look something close to this, just scaled on the X and Y axis slightly different. But you should have a scale, labels, data points, a best fit line. The next thing I'm going to show you guys how to do is to calculate the slope of this best fit line. Over on the right hand side of the page, I'm going to show you guys how to do the calculations for slope. I want you guys thinking about slope as a comparison between the Y data and the X data. And when I mean comparison, it's going to be the change in Y, which we represent with a triangle, and it's a division or quotient between the change in X. It's really a ratio between how much the Y changes and the X changes between 2 places on the graph. Now, a major misconception is that you guys are supposed to pick the data points for your work here, but that's not true. I want you guys to try to pick places, not points, far away from each other on the best fit line. In a best case scenario, you would pick a place that goes through the 4 corners of these grid boxes, but that's not always the case. Where my cursor is now, you could pick this place, but I'm going to go a little bit further away and estimate down here. And I'm going to call this approximately my place number 1. I'm going to go further away on the X or on the best fit line, and I'm going to pick another place to compare the change in. And again, along this best fit line, as I get out in the edges, no one place maybe crosses the 4 boxes, and maybe I'll choose that one here. This one's a little bit off, so maybe I'll actually bump it out to this one right here and call this spot number 2. These are not data points, they're places I'm picking. So I'm going to do the change in Y between spot 2. So I'm going to get the Y value from the the Y axis, and I'm going to subtract it from the Y value down here for this spot 1. And then I'm going to go and do the change in the X, where I get the X value from this spot, and I go over spot 1 and get this X value, and I subtract the difference. So when I think about change in Y compared to change in X, it's often written like change in Y as Y2 minus Y1, where Y2 is actually the Y value from spot 2, Y1 is the Y value from spot 1. And then you're going to divide that by X2 minus X1. And remember, X2 means it's the X value from spot 2 down on the X axis. X1 means the X value from spot 1. And so now I'm just going to go and try my best to estimate Y2 and Y1, and I'm going to write them down with units. So if I trace over spot 2, it's not quite up halfway between 90 and 100, so I might estimate this to be about 93 grams. So I'm going to write down 93 grams minus, I'm going to go to spot 1 to get Y1. Now this one also is almost halfway, but not quite. I might call that 4. Some people might call it 3. So there's my change in Y. Now let's go back to spot 2 and get the X value for spot 2. And luckily for us, I chose it on the grid line. So that's 11 cubic centimeters minus X1. Remember, X1 is the X value for spot 1, which is pretty much right on the grid line. So I'm going to follow that down to that interval, and it's 0.5 centimeters cubed. Now what we have to do is simplify these things. So if you guys look at my example, I'm going to do the change in Y. So if you take 93 minus the 4 grams, you get approximately 89 grams. If you guys subtract 11 and the 0.5, you'll get 10.5 cubic centimeters. Now, density is often reported out universally for every 1 cubic centimeter, because it's hard to imagine 89 grams of material for 10.5 cubic centimeters. So conventionally, we always simplify our slopes over 1, so we can say for every 1 cubic centimeter of volume. So I'm going to divide 89 divided by 10.5, and I got 8.48 grams. Now the calculator doesn't spit out any other numbers. You have to assume that this 8.49 is related to the numerator, and that there's this ghost 1 hanging out underneath. We need to put the 1 down here to hold the unit of centimeters cubed. So here is my density, my mass to volume ratio for the substance I measured. Now I could take this density and go and look online at a table of densities and try to identify what material type I had based on the color and the density, and the fact that I'm pretty sure that I'm going to call that a metal that I had. Now finally, the last thing you need on your graphs for today is identifying the y-intercept. The y-intercept is where the best fit line intercepts the y-axis. Sometimes your best fit lines will cross up here. In this case, your y-intercept would be approximately 26 or 27. But on my graph, my y-intercept is essentially the origin, and the y value at this spot is 0. So my y-intercept is 0 grams. And we'll talk at some point in class about whether or not that makes sense and is ideal under perfect conditions, or if there's major errors in my data collection. So review these steps, make sure your graphs look like this. This is a review from graphing for anyone who had physical science 9th grade year, and get your graphs up to date. If you got questions, come contact me or another science department member.